Hello students. In today's class, I am going to discuss about the stationary states. So stationary states are very useful in quantum mechanics, and let us discuss these states. So what are the stationary state basically? So if I have a say state psi, which is a function of psi, x, and t. So you have a space function and time function. If I can factorize this state or this wave function separately in space part and time part. So if I can write this function as a phi x and say tt, t is a function of time only and phi is only function of x only. So this because these type of states are called stationary states. Now what is the advantage of this state? For example, we have a Schrodinger equation, say iota h cross del, where the psi is a function of t, del t, which is equal to minus h cut square 2m del 2 psi is again function of x and t, x square, and now we have a potential energy which is again function of x and time t. Now if I take potential such that this is only function of x, which is true for many of the problems we are going to discuss in the quantum mechanics, then my time dependent Schrodinger equations become like this. Now if I calculate it, if I substitute this function here, so del psi xt upon say del t, this will give me what? It will give me phi x del t upon del t, which can be also written as a phi x. Now because we have ordinary differentiation will be function of t only, so this is a function of t only, so I can also write this as a dt. Similarly, if I calculate say del psi xt upon, which is a function of x and t both, del x, I want to substitute here square. So this will give me del 2 psi upon del x square will be again t. Now this will be equal to del 2 phi x upon del 2 del x square. Okay, del x square psi del x square. Now let us substitute these values in this Schrodinger equation. If I put these values here, what I'll get? If I put these values here, the Schrodinger equation gives me, say, I'm taking a line here. So now put these values here. So this will give me iota h cross t t. Sorry, this will give me now iota h cross del psi upon del t. So iota h cross phi x dt upon t and dt, this part, and here this will become simply minus h cut square, yes, psi xt also there, psi xt minus h cut square 2m del 2 phi upon del x square, and here you have Vx, which is equal to phi x and tt. Now if I divide this equation by phi t, so this will give me iota h cross d upon dt dt, and this will become t, and this will give me here, of course, tt also there because I have used this function. So now if I divide this one, this will become a 1 upon phi x minus h cut square 2m plus Vx. If I substitute this one, now this equation is equal. Now this is a completely depend on time and this is completely depend on x. Now this is only true when both equations are equivalent to a constant. Otherwise, what will happen if I change the t, this part will change, but this will not remain unchanged. That is not possible because both should be equal E. So in order to make equal E, I am putting this is both are equal to a constant E. Now let it separate this equation. So now I have say iota h cross del t upon del t. This is equal to say TE, and if I solve this equation, integrate this equation, ET upon iota h cut, so this equation will give me the time part is equal to e power minus iota ET upon h cut. These are the time part of the wave function. Similarly, if I see now the space part, x part. So what it gives me? This gives me minus h cut square 2m del 2 phi upon del x square vx phi is equal to e phi. Now we know this is equal to what? This equation can be written as a sh phi equal to e phi. That means what is h here? Here h is the Hamiltonian. H is what? H is the Hamiltonian minus h cut square 2m del 2 upon del x square and plus Vx. So this is the kinetic energy operator. So this is the H, this is the kinetic energy operator, and this is the potential energy. So kinetic energy, potential energy is equal to Hamiltonian. So this equation suggests that phi's are the eigenfunction of Hamiltonian. Now, so now what become my psi xt? Now psi xt becomes psi xt can be written as a phi x e power minus iota et upon h cut. So these are my stationary states, and why these are called stationary states, and what is the why these are so useful. So let us see their properties. If I calculate probability density with the states, so if I calculate say probability density, which will be equal to psi xt mod square. So this time part will be cancelled out. So this will be only equal to pi x square. That means the probability density of this function is time independent. So this is a time independent stationary. Time independent means stationary. So probability density is time independent. Similarly, if I calculate the expectation value of any operator or any function of x or p, then what I can write? I can write this is psi q, which is a function of x, and say iota h cross del upon del x momentum psi dx. This will be also independent of time. So if you get the position expectation value of momentum, position, energy, these all are time independent. So expectation values in these states are also time independent. Expectation values are time independent. This is the first property. Probability density is constant time. Expectation values in these states are independent of time. And now these states are of definite energy. These states are of definite energies. Just now I told these for this equation you have a h phi equal to e phi. So if I calculate the Hamiltonian average of expectation value Hamiltonian, so what will become? This becomes psi star xt and Hamiltonian, and psi is your psi xt dx. Now what will happen if I calculate this one? Psi xt time factor is independent of x, and h will not act on this one, so this time factor will be disappear. So only this we will left only with psi xt h psi x dx, and now this is already e, so this become e phi star x phi x dx. If these are normalized, so this is only equal to e. And if I similarly, if I calculate say h square, if I calculate say I have say h, say h psi is equal to what? H psi is equal to psi is e power minus iota e t upon h cut, and this will be h phi, which will be e phi. So this is equal to e phi. Similarly, if I apply now h square psi, so this become e square and you are operating one more time. So let us operate here. So we are operating h square. So let us calculate now mod of h square. Mod of h square. So this will be what? This will be again phi star psi star xt h square psi xt. Okay, again I am taking this time part cancel out, so this will be phi xt phi x and h square phi x. And now if you operate this on 2 times, so this will give me simply e square, and this is a normalized function, so this will be e square. And if I now calculate the variance of h, this is delta h. So what will come? Variance of h will be say h square minus expectation value of h square, and this is equal to e square minus e square 0. So these are the properties of these stationary states. Now we know that time independent Schrodinger equation has infinite solutions. So any general solution, say psi xt, can be written as a superposition of these infinite states. So I can write here, this is Cn, and this is my Cn xt, where I know what is Cn, and psi n is my phi n x e power minus iota e and t upon h cut. So any general solution of time dependent Schrodinger equation where the potential is independent of time, that is important. Potential should be independent of time. Then any solution can be written this way. We can first find psi x0, which is equal to n Cn phi n x, where phi n and phi n's are what? Phi n means phi 1, phi 1x, phi 1 2. So for example, if I want to write say this psi 1x, psi 1xt, psi 1xt will be what? Psi 1x will be phi 1x e power minus iota e1 t upon h cut. Similarly, you can write psi 2 xt will be phi 2x e power minus iota e2 t upon h cut, so on. So these all are the solution of time independent time. These are the all solutions of time independent Schrodinger equation, and a general solution of time dependent Schrodinger equation can be written here like this, where Cn's are what? If I make this function normalize, so this gives me the condition mod of Cn square should be equal to 1, where Cn square is what? Probability of measurement of En. Probability probability of measurement of value En. So if you measure, you'll in the measurement you'll get the value En. What is the probability? So the probability is given by this constant we have discussed also in the last class also. And now if I want to write the expectation value of Hamiltonian, that will be simply equals to Cn square En. So here we have the time dependent, here we have the stationary states, which are the eigenfunction of Hamiltonian. So we can write like this way, but this is true for any operator. If we can express the wave function as a superposition of stationary states of any other operator, then this is true for any other operator. So if I have any other operator, this one, so I can also write Cn square, and then this will be the other operator where Cn square is the Pn, probability of finding the energy En, the state. So, and these stationary states will occur when we'll do different one-dimensional cases of like potential, like in a particle in a box, step potential. Now we are seeing these states are stationary state, but what about the superposition state? Whether the superposition is a stationary state or not. So let us check with an example. Say if I take the superposition of two stationary states, say I have a psi x0, say which is the superposition of two state, say C1 phi1 x plus C2 phi2 x, or psi xt. So psi xt will be what? Psi xt will be C1 phi1 x e power minus iota e1 t upon h cut. So C2 phi2x e power minus iota e2t upon h cut. And now if I calculate the probability density psi xt square, so what it will give me? It will give me C1 square phi1 x mod square. If I multiply this one with this one, and C2 square, and this will be mod of phi2 x square. And if I similarly, if I solve this one, so this will give me C1 C2 to directly writing this will be 2 C1 C2 cos of, I'm taking the real part only, real part. If you multiply this one, this will give me cos E2 minus E1 upon h cut t 2 C1 C2, and then you have your phi1 also phi1 x phi1 phi2 cos E2 minus ET h cut. So these states are not stationary because they are oscillating with a frequency. This is a frequency. So these are oscillating with a frequency E2 minus E1 upon h cut. So that means superposition of stationary state not necessarily be a stationary state. However, if we take here E2 minus E2 is equal to E1, then that is also station state. But in general, superposition states are not your stationary state. So that was station state mainly covered from the Griffith book. So hope you understand. Thank you very much.